Hello and welcome back. And today we have, it's not a math puzzle, I'm gonna say it's kind of a challenge. Which would be your choice? And you have two choices. One is getting $1 million total and lump sum in your hands, or another option, I'm gonna give you 1 cent, 1 penny, and then the next day I give you another one, so you have double. The third day I give you 2 more, then you're gonna have double, have 4. And every day I give you more pennies, so you have double the amount you had the day before. For 1 month, 31 days. What would be your choice? To have the $1 million in your hand, lump sum, just once, or to have the pennies for 1 month, day by day, increasing the total amount, doubling every day until the last day of the month. And think about it. Maybe it's an easy answer, maybe it's a tricky question, I don't know. Later, at the end of the lesson, we're gonna go back to this challenge, because today we will work on chapter 7, rational exponents, radicals and complex numbers. Section 7.3, simplifying radical expressions. The first objective is to use the product rule for radicals, and let's understand what is the product rule. If you have the nth root of A and the nth root of B as real numbers, then you can write like n root of A times n root of B is going to be equals n root of A times B. Very simple rule, but it's going to be very useful to simplify radical expressions, as we will see later. Okay? And a few examples. Letter A, square root of 3 times the square root of 5, and we can write this as the square root of 3 times 5, which is equals the square root of 15. Next, the square root letter B. Now I have cube root, cube root of 4 times cube root of 2, and the index is 3 for both cube roots, and we can multiply. We can use the product rule and write this as cube root of 4 times 2 is cube root of 8, and we know that cube root of 8 is 2, right? And example C, square root of 2 over A times the square root of B over 3 is equals to the square root, and inside we're going to have 2 over A times B over 3, and that's it. Numerator is 2B, denominator is 3A. This is how we apply the product rule. Now the next objective, number 2, is to use the quotient rule for radicals. Now we have again the nth root of A and the nth root of B that are real numbers, but just make sure that the nth root of B is different from 0, okay? So we can say that the n root of A over B can be written as the nth root of A over the nth root of B. Now a few examples to work with the quotient rule, and let's get another color. Great. Now we have square root of 5 over 16. We can apply the quotient rule. So we have a square root of 5 over a square root of 16, right? Square root of 5 we cannot simplify, we just keep it like this, square root of 5. But square root of 16 is something that we can simplify. This is equals to 4, and that's going to be the answer. Square root of 5 over 4. Now, square root of 40 over 81. All right, we can write this as square root of 40 over square root of 81. And can we simplify? Can we do something to make it nicer and simpler? Well, we can rewrite this. Let's say 4 times 10 over, and the square root of 81 we know is 9, right? Here on the top we can simplify because square root of 4 is 2. Square root of 10 we cannot simplify, that's it, it's 10 over 9. That is the answer. And let's work on a few more examples. Let's say now we have cube root of 27 over 64. So we can apply quotient rule. This is cube root of 27 over cube root of 64. Okay, and let me just divide this and use this side of the screen to solve letter A. What is the cube root of 27? If you know, is 3 cubed is 27, so the cube root of 27 is equals to 3, and cube root of 64, 4 cubed is 64, so cube root of 64 is 4. This is the right answer. Now letter B. We have here fifth root of 7 over 32x5. We can apply the quotient rule, so it's the fifth root of 7 as the numerator and the fifth root of 32x5 on the denominator. Okay, let's work this, and let me just fix this thing. This is equals to, we cannot simplify the fifth root of 7, just repeat the numerator, fifth root of 7, but on the bottom we can apply product rule, the reversed or backwards, because we can write this as 50 root of 32 times fifth root of x5, right? This is equals fifth root of 7 over fifth root of 32 is 2, fifth root of x exponent 5 is x. That means this is the answer. Now we're moving to the next objective, number 3, simplify radicals. Let's go straight to a few examples. We can use the properties that we just learned to simplify those radical expressions. Okay, let's try to apply the first one, letter A. You have to break down 40 into a multiplication of numbers in a way that you can simplify. You can find the perfect squares that you can remove from the square root, from the root. Okay, so we are talking about square roots. We need to find perfect squares, and 4 is one perfect square, right? And we can break down 40 as 4 times 10, because now we can apply the multiplication property, the product rule for radicals that we've seen at the beginning. The square root of 4 times the square root of 10, and this allows us to simplify and have 2 times square root of 10. Another example, check this, letter B, and we have the square root of 300. Think about a number that we need to break it down and find at least one perfect square to simplify, and we can write this as 100 times 3, right? Because 100 is a perfect square, and applying the product rule, we will have square root of 100 times square root of 3, and the square root of 100 is 10, right? So it's 10 square root of 3. And there's also example letter C. Now think about it. 15, can we break down in any number that is a perfect square to be able to simplify? Well, let's break this into the prime numbers, and 15 is 3 times 5. That means this is the most that we can break down 15 into, and there are no perfect squares. We cannot simplify it. So it's already simplified. This is the simplest way we can represent the square root of 15. More examples. Now we have some cube roots. Simplify each radical. And the first one, can you think about a perfect cube that you can break down 16 into? So we're talking about cube roots. Now we need to find perfect cubes. And definitely 8 is a perfect cube. If you multiply by 2, you have 16, right? But you can apply the product rule for radicals. Cube root of 8 times cube root of 2, and the simplification results as 2 cube root of 2. That is the answer. Letter B, cube root of 3 over 64. And think about it, how can you simplify? We can write this cube root of 3 over cube root of 64, okay? Now think on the numerator, there's nothing we can do because 3 is already a prime number, we cannot break it down, but maybe on the denominator, there's something we can work out. And the denominator, cube root of 64, 64 is actually a perfect cube. It's 4 cubed, right? So we can find the cube root of 64 as 4. That is going to be the answer. This is equals to 4. Cube root of 3 over 4. Right, and now examples to simplify each radical and assume that all variable expressions represent positive numbers. Now we're going to work with some variables, and remember those variables are positive numbers. So check this first one, the square root of x exponent 7 we can write this down as the square root of x. We can break x into, let's say, x6 times x, and write like this: square root of x exponent 6 times square root of x. We are able to simplify this as square root, not square root, as x. If you apply square root here, you're going to divide the exponent by 2, right? This index is 2, and then you have x cubed times square root of x. This is the answer after the simplification, the results that you will find after you simplify the expression. Now another radical expression, letter B. Square root of 20 over x exponent 16. We can break it down as square root of 20 over square root of x exponent 16. 20 is, we can break it into a perfect square, 4 times another number 5 over, and remember this is a square root, right? The index is 2, and we have x exponent 16. We can simplify, we can find an answer here by dividing this exponent 16 by the index 2, and this is x 8, and on the top we can write like this: exponent 4 and radical square root of 4 times square root of 5. This is 2 square root of 5 over x exponent 8. Okay? All right. This is interesting because we get from very kind of it's a bit complex radicals, expressions, and we can simplify and find smaller numbers, simpler expressions. That's the whole point. Now, a very interesting example, and we have here cube root of 54 times x exponent 6 times y exponent 8. Let's check how to simplify this. The thinking is, look at that. We have cube root and 54 we can write as, can we break it down? This is the first question. Can you break down and find the perfect cube? That maybe we can simplify. And yes, the answer is yes. 27 times 2 is 54. And we know that 27 is, and let me write here, 3 cubed. That means 54 is 3 cubed times 2, right? And x 6 and y 8. The whole point is we can also break down this y8 as y6 times y2. Okay? And those that have the exponent as a multiple of 3, we have 3 cubed, x6 times y6, we can write like this. Tell me if you understand. 3 times x squared, y squared, in it, all this whole thing cubed, and we still have this 2 times 2 times y squared, right? Is cubed. And we can simplify, we can remove this using the product rule, we can write as, well, I'm showing all the steps so we understand what you're working, but when you get some practice, you can skip a few steps as long as you understand, you're confident on what you're doing, times cube root of 2y squared, right? And this we can simplify. Look, we can make this, let me just erase, 3x squared y squared times cube root of 2y squared. That is going to be the answer after all the simplifications that you can work out on the radical expression. And we have a few more examples. Use the quotient rule to divide, then simplify if possible. Assume that all variables represent positive real numbers. That's fine. For the letter A, we just have numbers, and this is okay because we can write this. Let me split the screen, and we can write 20 as the square root of 4. Remember, times square root of 5. Remember this? And here at the bottom we have a square root of 5 that we just can simplify, cancel out. And the answer after simplification here is the square root of 4, which is equals to 2. That is the answer. On the example of letter B, we will apply the quotient rule backwards. And we're going to put together, let me show, we have 7, this is equal 7, right? And we're going to put together, because they have the same cube root on the numerator and denominator, so let's put together this numerator and denominator inside the cube roots to check if we can simplify something, okay? We can do this. This is the quotient rule applied backwards. Now think about it. We can simplify 48 with 2, which is 24. And we can simplify this y on the denominator, subtracting 1 from this exponents on the numerator. So we will have as a result 7 times cube root of 24 y cubed, and the denominator is gone. We don't have anything anymore on the denominator, right? We just cancel out everything. Very good, because we have 7 and we're gonna have 24. You can multiply, you can break it down and have one perfect cube, like 8 times 3 times y cubed. And this is equals, let me show just every step 7 times. Apply now product rule, okay? Cube root, I forgot the cube here, cube root of 8 times cube root of 3 times cube root of 1 cubed, right? This is the cube root of 8 is 2, and this we cannot simplify, but cube root of y cubed is y. So the answer is 7 times 2, 14 times y times cube root of 3. Or better, and if you write down all the numbers up front and the variables afterwards. This is a better way of writing this answer. Okay, now we have a new objective. Number 4, use the distance and midpoint formulas. By using Pythagorean theorem, we can derive a formula for finding the distance between 2 points. And the formula is going to be, we will use on the formula the coordinates of point 1, x1 and y1, and the coordinates of point 2, x2 and y2. We can say that the distance is going to be equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. If you are curious, you can derive this formula. You can apply a Pythagorean theorem. If you draw the graph on the rectangular coordinate system, you're going to be able to see the right triangle and check all these elements that we're using on the formula. And we will apply on an example. Find the distance between the 2 points, x equals -5 and y equals 8, to the other point, x equals -2, y equals 2. You can say this is point 2 and this is point 1, doesn't matter, it can be either way. And the formula of the distance is x2 -5 minus x1 minus -2 squared plus y2 is 8 minus y1 2 squared. Okay? And after you simplify, you're going to find d equals -5 minus -2, negative and negative positive, so -3 squared plus 8 minus 2, 6 squared, and this is equals to 9 plus 36. Distance is square root of 45. And this is not a perfect square, but we can simplify because we can write 45 as 9 times 5, right? And square root of 9, 3 times the square root of 5. This is the answer after the simplification. Next, let's have a look at how to find the midpoint of the line segments. And to calculate the midpoint of the line segments, we have also a formula, a way of calculating. If you have the points 1 and point 2, so you're gonna calculate the coordinate, the x-coordinate as x1 plus x2 over 2. This is the x-coordinate, and the y-coordinate y1 plus y2 over 2, right? This is the x-coordinate of the midpoint. This is the y-coordinate of the midpoint. Let's check an example. And if you have the points, let's say this is point 1, this is point 2, so we can calculate the coordinates of the midpoint. X1 plus x2 over 2, and y1 plus y2 over 2. The result is going to be -5 minus 2, -7 over 2, -7 over 2, and 8 plus 2, 10 over 2, 6. Those are the coordinates of the midpoint, right? And this is the end of section 7.3. What is your answer now for the best choice? You have to select the choice that gives you the most money. And let me tell you, the first choice, you don't have any questions, right? It's just 1 million lump sum. The second one, you're going to have, the first day you have 1 coin, which is true exponent 0. The second day you have 2 coins, is true exponent 1. The third day you have 4 coins, true exponent 2, and this goes on and on. On the first day, you're going to have 2 exponent 30 coins, true exponent 30. This, if you try in your calculator, is going to be more than 1 billion coins. And if you find the amount in dollars, multiply by 1 cent, right? 1 penny, 1 billion coins times 1 penny, and then you're gonna find more than $10 million and on this option with the pennies. Well, this is just a game, and to understand one topic in math that's called exponential growth, that involves exponents. Well, thank you for watching this video, and hope to see you soon on the next section.